Good morning, everyone, and welcome to the EVENFLOW Use Case Webinar on Personalized Medicine, focusing on breast cancer challenges. My name is Davide Cirillo. I am the Communication Officer of EVENFLOW Project. We are delighted to have you join us for this insightful discussion on how artificial intelligence and forecasting techniques are being applied to address breast cancer. I would like to inform you that interaction via microphone and camera is disabled to ensure the smooth flow of the event. Therefore, we encourage you to submit your questions via the chat during the presentations, and they will be addressed during the Q&A session. So today we are honored to have some distinguished speaker, Dr. Miguel Quintela, a leading expert in breast oncology, and Dr. Davide Cirillo from the Barcelona Supercomputing Center, who specializes in personalized medicine and AI. But first, I would like to welcome EVENFLOW coordinator, Thanasis Poulakidas, who will briefly present EVENFLOW project. So, Mr. Poulakidas, the floor is yours.
Thank you, Faye, and thank you all for preparing this webinar. Let me share. I will say just a few words on this project. I hope you can see my screen now. Can you see my screen?
Yes, we can.
Okay. Just a few words about the project so you know what the content of this webinar. This is a project, a 3-year project. We started in October 2022. So we are now entering our last year of this project. The project is has to do about trying to have complex event forecasting, right? And we want this to be with learning and reasoning techniques and to be robust. Okay. It is a very focused project with a very focused consortium, as you can see, only 7 partners, but we believe that it is highly proficient and does a great work on that. Our technical way of sorry about it. Our technical way of working, of moving forward, is to try to get, let's say, simplistically speaking, we try to get from data streams coming from sensors, perception level information, data sets, or everything, simple data, where we build event-based primitives, and then we build on top of that, we try to make the forecasting of critical situations. And then we want this to be explainable, and then we want to build on this explainability to have intelligence, proactive intelligence. Okay. Then this is this case a lot of neural processing and a lot of neural symbolic processing in these stages. And to this, we have 2 more lines research. One has to do with verification, where we don't just get the input data, we only create in a very careful way perturbations of this input data. So we have more different kind of inputs, and we try to test based on these inputs our solutions. So if that works, that means that our solutions work in a very much more robust way, and then we certify or we retrain and we adjust to the problems. That's one line of research. The second line is about scalability, where we look at scalability, what we call horizontal and vertical, have to do with, let's say, summarizing data. So instead of getting huge volumes of data, we only send synapses of them, or vertical scalability, which has to do about the speed of the data, and federated scalability, which has to do with the training of and all these kind of federations training. So with these 3 lines of research, the technical vision is to have robust and scalable pipelines for new symbolic learning to have explainable event forecasting. That's in a nutshell about the project is about from the technical point of view. Okay, the use cases, of course, today we have a webinar about the first one. It's about personalized medicine and how we can use about tumor growth, for example. We have 2 more use cases for your information. One has to do with an infrastructure life cycle assessment, and in particular, we'll look at water infrastructure, water pipelines in cities or networks, and how we can predict and foresee any failures. Okay. And the third use case is the Industry 4.0 use case, where we look at the robots working in factories, doing some tasks, and how we can make them, we can improve the work in a more robust way. Okay. Then these are the use cases. I don't want to say any more about this project. You are welcome to visit us, contact us in any other ways. This is a webinar about a very focus on the personalized case. So I would like to leave the floor to the experts on this. Thank you very much.
So thank you very much, Mr. Poulakidas. Now, Dr. Quintela will talk about breast cancer and current challenges. Dr. Quintela is a physician scientist specializing in breast oncology, integrating clinical practice with laboratory research. Currently, he serves as the group leader of the breast cancer unit at the Spanish National Cancer Research Center and as director of the clinical research program. Additionally, he holds a dual appointment with the Hospital 12 de Octubre, where his clinical research activities are based, and serves as an associate professor at the endowed chair in personalized and precision medicine in the Autonomous University of Madrid. His research has led to significant discoveries, including advancements in liquid biopsy techniques, among other contributions implemented in clinical trials. Dr. Quintela, please go ahead with your presentation.
Okay. Thank you. Thank you for the introduction. A second until okay. I think that you all can see my screen now.
Yes.
All right. Well, thank you everybody for being here today. When me and David tried to put together with this seminar, we realized that it was not an easy task. We both realized that we come from very different backgrounds. However, we had in common that we both wanted to illustrate how with this methodology we can make some aspects of these fields come together and actually solve practical challenges. And we thought that discussing breast cancer could exemplify the potentiality of some of these use cases. In whereas physicians, we think that we have a lot of hope in how new AI techniques can actually improve what we all want, patient experience, right? So I'm, of course, more used to present primary data and results of our research. Here, however, I'm going to try, to zoom out and just discuss a brief overview of a few main challenges that currently breast cancer patients face, in where we think that actually it's going to be the evolution of AI techniques or technologies, of course, together with other developments, what can actually improve or break the current plateau. So some of the things that I will discuss will be just plain facts, but of course, if any of these facts features require some deeper explanation, I'm more than happy, to provide more justification or background in the question round. So, starting from, let's say, the earliest history to the latest history of just a single cancer from diagnosis to death, I would say that the first challenge that we face right now, in where we have actually achieved a plateau that is not improving since more than 25 years, is make screening more accurate. So right now, these are European guidelines, also North American guidelines. This is basically enforced in most of the Western world. It is recommended or provided by all healthcare system so that women between 50 and 70 years undergo a yearly mammography. Fine. So this can vary 5 years up, 5 years down, depending on which region you live or the national coverage. So all this spans from studies performed in the early 90s. The result of doing mammography screening is tangible. There's metrics about this, and basically you achieve a 15% reduction in mortality. This means that you have to have roughly 1,000 women undergoing yearly screening to save 1 or 2 deaths if these women are going through screening for 10 consecutive years. Okay, so what happens? We have not been able yet to cure all these cancer cases by making diagnosis early. Here, novel technologies of image analysis have improved, let's say, superhuman capabilities of capturing very early cases. And this is very promising. I mean, lesions that escape the eye of the radiologist are identified by novel AI-powered imaging analysis technique. However, what is happening here? This has also a minus. In the studies that were performed in the 90s, that are actually the seminal studies that justify current screening policies, what happens, as you can imagine, these were designed as double-blind, randomized clinical trials. Well, not double-blind because obviously patients knew whether they were undergoing a screening or not. But basically what happened is that in the initial years of the trials, the patients that were randomized to have a yearly mammography, they started being diagnosed more often of early cancers. So the incidence that were diagnosed in the experimental arm was much higher. Doctors expected that in the control arm, in other words, patients not undergoing mammography, would start showing up with a higher incidence a few years later. So the tumors that were occult because we were not doing mammographies in these people would show up later. However, this didn't happen. What does this mean? That a lot of these so-called early cases that we were detecting were actually benign cases that would never turn into aggressive full-blown tumors. So we reduce a number of invasive full-blown tumors thanks to the early diagnosis, but the images that we see very often correspond to tumors that would never grow, and we are unable to distinguish them. So hopes are put in better image analysis techniques that are able to tell apart what the human eye is not, and combination maybe with liquid biopsy technologies, genomic scores, etc., so they can improve this index. And once we see a lesion in a mammography, we can tell whether this is actually a success of the screening and we have to remove that lesion, or whether we have to just leave the patient alone. This is an unmet need nowadays, the excess of diagnosis. In addition, there's another issue derived from this, and is that well, when 25 years ago, when I started in oncology, this disease was a disease of, let's say, grandmothers. And then this started shifting towards mothers, and now it's actually turning into a disease that is often diagnosed in daughters, women from in their 20s, 30s, very often in their 40s. What happens? Mammography doesn't see well through young breast. It's an issue of the mammary gland density. This is a test that was designed for the mammary gland of elder women. So younger women, in order to be diagnosed, they need other technologies, MRI, ultrasound, etc. So obviously, these technologies don't have the necessary throughput to run a countrywide screening. So of course, more advance in image analysis is needed, desperately needed, for younger women, which is right now the highest incidence of breast cancer. A second issue is, once the tumor is diagnosed, whether we have good or bad biomarkers in order to make treatment tailoring. What does this mean? That up until not so long ago, women with early disease were all treated the same. Then with the definition of the first, let's say, easy biomarkers, histology biomarkers, such as the hormonal receptor status or the HER2 status. This allow the division of tumors in three main subtypes: hormone positive, HER2 positive, or triple negative, and this allows some degree of treatment tailoring, more endocrine-like treatment for hormone positive, more anti-HER2 for HER2 positive, and more chemotherapy for triple negative cases. And then the development of genomic platforms further refined these subtypes, and actually it was revealed that the main subtypes defined by gene expression, namely luminal A, luminal B, basal type, or HER2 enriched, more or less 70–80% correspond to the main subtypes defined by estrogen receptor, progestin receptor, HER2, or the lack of all three. As a result of this genomic analysis, several genomic score platforms were developing. The most common, famous of them is Oncotype DX, was actually the first one, which actually, to the early tumors, it gives a score from 0 to 100. And according to this scoring, below 21 is considered low risk, above 21 is considered intermediate or high risk, okay? So on the basis of these scores, further tailoring is made, but this tailoring is not rational. For example, what you see here, and this is the only primary, let's say, data that I show here, what you see here in the far right is for the patients with hormone-positive breast cancer, this is the long-term probability of being cured if you have a low risk oncotype score. So even here you see that in the long term, more than 10% of the cases relapse despite being low risk. What was compared in this trial is in low risk patients being allocated to just hormonal treatment or hormonal plus chemo. As you can see, the curves overlap, and this is a good advance. The result of this advance is that the majority of patients, which are actually, this is what we have out of the screening, hormone positive, low risk, these patients no longer need chemo. And this is a good advance. We know that we don't need to give them chemo, which is a toxic treatment. But still, we fail in terms of that 10% of these patients are not adequately classified. They still relapse. And as you can see, chemotherapy doesn't rescue them. And if we go to the high risk, these curves are way more disappointing. The relapse rate is closer to 30–35% just with hormones. Chemo reduces this to maybe 20%. So clearly, we're not giving a specific treatment. We know from this platform that these patients are not responsive to hormones alone, but we don't really know what to give them. We just give them empirical chemo. So we need better refinement of these prognostic scores. And if possible, these prognostic scores should also inform about which therapy does this patient require rather than non-specific chemo. Next, unmet need, and here we shouldn't call this AI, but just playing standard bioinformatic techniques. The advances of NGS analysis have allowed an improvement on what happens after a patient has been treated for from an early tumor detected by screening or by autopalpation or whatever. So as you saw in the previous slide, depending on the tumor subtype, 10–30% of the patients relapse. So obviously, the experience tells us as oncologists that early tumors, localized tumors can be cured, but advanced tumors with metastasis in different sites is very tricky to cure them. So in principle, we would like to invest as many resources in treating and curing patients in the early phases of a tumor. When you have diagnosis of full-blown metastasis, is very difficult to manage these patients. So in the late 90s, the initial efforts were directed to try to detect microscopic disease, distant microscopic disease, before it turned into macroscopic that could be detected by CT scan. So the initial attempts were made in detecting circulating tumor cells, and of course with the development of NGS, the focus shift to, rather than detecting circulating tumor cells, circulating small fragments of DNA that have aberrant sequences that, of course, would not come from healthy tissue, but would be shed from the mutant tumor cells. So in this sense, the specificity of these techniques is broadly very good. Detection of CTCs is usually, let's say, unequivocal. However, a lot of patients that relapse never show, at least with current techniques, never show peripheral CTCs. But basically, if you detect CTCs, that patient is at 4 times higher risk of having a relapse. This is usually detected with machines that combine optical microscopy and fluorescence. NGS-based techniques, if you detect in a patient that has been recently treated from an early tumor, if you detect mutant P53, mutant KRAS, etc., in peripheral blood, the risk is very high. I wouldn't say it's 100% sure you're going to relapse, but the risk is roughly, depending on the series that you look at in the literature, but the risk is around 10-fold higher for those patients with mutant transcripts in peripheral blood. So specificity is very high. It's very rare that you show up those transcripts in peripheral blood and you don't relapse. However, sensitivity is low, meaning that we still have patients that relapse in whom we have never detected these transcripts in peripheral blood. So this is probably a technical challenge rather than an analytic challenge, but still, if you go too deep in the sequence, you're going to have issues with your analytics. So here we need both better technologies, such as beaming and all these new developments, but of course we need better bioinformatic pipelines to avoid noise. We have already achieved very high specificity, so we should not lose this specificity when we start looking deeper and deeper with higher sensitivity. The last point is not something that I think that we could probably solve with AI technologies right now, but who knows? And it's the thing that there has already been a couple of pioneers that have started to make intervention the moment that patients were detected to have this residual disease in peripheral blood, this microscopic disease. There has been a couple of randomized trials in where the patients were randomized the moment they show up micrometastatic disease in peripheral blood to receive further treatment or just continued surveillance. And for now, none of these trials has resulted in a delay in the diagnosis of overt full-blown macroscopic metastatic disease. And actually, this has been tried with immune therapy and it has been tried with chemotherapy. This probably means that the mechanism of cell survival, the mechanism of action of distinct chemotherapies and immune therapies is different for isolated tumor cells than for established tumor mass. But this is something where more research has to be done. However, it's difficult to play with these models. It's not very easy to make models of micrometastatic disease. The next challenge, and it's probably one of the more important right now that we're dealing with, is once a patient has experienced a relapse, is the issue of treatment resistance. Usually when you treat a localized tumor, as we show in previous slides, most often you can clap your hands and claim success. Most of the times tumors are cured. However, in advanced disease, you apply long-term courses of very intensive treatment, and almost invariably, you end up finding resistance, tumor regrowth. The problem here, as you may imagine, is that tumors are very heterogeneous. Tumors have within their tumor cell population very distinct genomic makeups, but that's not the only reason. It's not resistance is not just the result of clonal selection in response to selective therapeutic pressure. Recent developments and research show that many features play a role in acquired resistance. And just to name a few, these mechanisms span from features derived from tumor microenvironment, such as the presence of inflammation, the activity of the immune system, or even metabolic characteristics of or features unique to the tumor microenvironment that can actually modify epigenetics, etc. Epigenetic itself is a major driver of phenotypic plasticity and adaptation to treatment. So not everything has to be selection of new clones. It can be just the adoption of the dormancy state or shifting back and forward in the cancer stem cell spectrum. Similarly, there's external factors that play a role in the acquisition of resistance, such as diet factor, exercise, etc. So this has been shown. Obese people have higher relapse than those that are leaner, the same with people that is sedentary, and so on and so forth. So the integration of all these factors requires not only experimental modeling, but also machine learning and AI techniques that allow to tackle the weight of each of these factors and actually identify at the individual level which of these factors is actually determining the clonal drift or the epigenetic drift or whatever is happening in that particular moment. Because if we are not able to individualize this, it's not going to be possible to anticipate the evolution of tumor treatment resistance and actually be able to chronify or to eliminate the disease. In fact, 20 or 25 years after research started in this field of trying to tackle tumor plasticity, it's still hard to say for an individual case whether the resistant phenotype is the result of tumor clones, or I don't want to focus too much in saying that are different clones. It's not all genetics here, but tumor cells that were already resistant and represented a small fraction of the tumor beforehand and just outgrowth after prolonged treatment pressure, or if it's just random events that happen. There's no initially resistant cells in the tumor, but with time, some of them become resistant. Actually, the funny thing is that both models have been proved preclinically. So I don't know if it's just an artifact of our research or it's a real fact, but everything seems to make things more complex. And entailed with this, of course, is the fact itself, and I think to me this is the more complex, the issue of tumor heterogeneity. Is not just understanding the tumor cell to tumor cell variability, which it is there, not all tumor cells behave the same, but also how the tumor as a whole organ behaves. Because in a tumor, you find, maybe 50, 70% of tumor cells, but you also find fibroblasts, which show up, display like 5 or 10 different phenotypic traits, all of them promoting or inhibiting some tumor progression features. The same can be said with the tumor immune cell infiltration compartment, and the same can be said for endothelial cells. Endothelial cells are as well involved in the tumor trophism and tumor evolution and tumor dissemination steps. So all these interactions make a chaotic but still very fit organ that up until now it has proved to be very difficult to understand, in terms of that whatever you just do in isolated tumor cells in your preclinical experiment most of the times doesn't translate accurately when you are not modeling anymore, but applying those findings to the complex organ of a tumor that is actually constituted in a live patient. Is much more complex. So right now, many single-cell RNA-seq technologies are starting to define populations, niches, etc. But I actually, each time I read one of these papers, I feel more and more worried because I see a lot of dynamism in these populations. They seem to shift back and forth in response to treatment from tumor promoting to dormancy states very easily to support tumor growth, no matter which is the environmental constraints or metabolic constraints. And actually, so far, whenever we try to tackle this issue derived from tumor complexity, we always have the feeling of being running behind tumor evolution. So this goes hand by hand with the previous feature, and I think that these are probably the two main challenges that metastatic patients face. This is my vision of the main challenges that I think that working hand by hand with biocomputational scientists, I think that we can actually make real and tangible advances for cancer patients. So happy to take any questions, and thank you very much for your attention.
So thank you very much for your presentation, Dr. Quintela. Next, we have Dr. Davide Cirillo, who will discuss how AI is being applied to personalized medicine through the EVENFLOW project. Dr. Cirillo is the head of the Machine Learning for Biomedical Research Unit at the Life Sciences Department of the Barcelona Supercomputing Center. His research focuses on computational methods for precision medicine, with a special emphasis on machine learning, network science, and ethics of artificial intelligence. He is the co-editor of the book titled Sex and Gender Bias in Technology and Artificial Intelligence, Biomedicine and Healthcare Applications. So, Dr. Cirillo, please go ahead.
Thank you, Faye, for the nice presentation, and thank you to the EVENFLOW project and the organizers of this event, which is incredibly interesting. So yes, now we are going to talk about specifically the personalized medicine use case of EVENFLOW project that is focusing on breast cancer. But I would like to start by essentially setting the stage, illuminating the fact that this use case is tackling like a challenge, which is a major challenging biomedicine, contemporary biomedicine nowadays. So definitely relevant for breast cancer research, but also in other contexts. And I'm referring to the fact that is actually has been already touched upon by Dr. Quintela. I'm referring to the fact that biological processings, including pathological processings, of course, have a temporal dimension attached to them. So we were just talking before about dynamism. And this temporal aspect is quite often neglected. Of course, like the type of data that the type of observation that we can get from the data that we have give us snapshots of these processes, either if we look at a macroscopic level, like for instance, those images that you can see on the left, in which you can observe throughout time the growth of breast cancer, but also if we look at microscopic levels. So for instance, these are on the right, we have a diagram of a signaling pathway that consists of a series of steps that leads to the activation of a transcription factor that migrates to the nucleus and modulate the expression of genes that can be important, for instance, for breast cancer progression. So in both cases, there is a time component that we have to factor in. And depending on the type of data, we have to basically find ways of filling the gap and understanding how to reason about these temporal progressions, right, at different scales. So I would say that the personalized use case, the personalized medicine use case of the EVENFLOW project has an overarching question that is, how can we accurately reconstruct temporal processes that are important for cancer research from just a series of snapshots, like the type of data that we generally have available? And we can, this question is emerging more and more, for instance, in the domain of single cell. And it has like explicitly said before by Dr. Quintela, like this dynamism, that can be captured from this type of data. And so, like, if we were to apply those concepts and those technologies, those methodologies, also to other type of data, there are some lessons learned from single cell dynamics that we can get. So first of all, we need to find good ways of representing the data that we have. And for instance, in single cell, artificial intelligence approaches, in particular representation learning approaches, are used in order to find lower dimensional representation of all those cells that can illuminate, for instance, about the different states in which those cells that has been collected in a specific moment in time are. And so, for instance, as you can see here, by analyzing those states, we can derive insights on the process of development that goes from the progenitor to more differentiated cells. So data representation is important. And another, let's say, lesson that we can learn from the field of single cell related to, disentangling the temporal aspects of biological processes is that we can operate on top of this data representation by applying a series of mathematical approaches, like, for instance, in this case, optimal transports or other, in order to have trajectories, in order to derive what we generally call the pseudo-time trajectories. That, for instance, in this case, once we have like a measurement snapshot, can allow us to understand, for instance, the impact of a perturbation, like, for instance, a treatment, a drug, a therapy, in a population of cells. So data representation and operations on top of these representations. And those are basically the ingredients that we are applying to the personalized medicine use case in EVENFLOW when we tackle specifically breast cancer. Actually, what we are very much interested into studying are the molecular determinants of cancer staging. So this is of course, a temporal process in which the tumor grows, and actually the different stages, which generally are labeled from 1 to 4, really reflect the size of the tumor and also the level of invasion, if you want, of the surrounding tissues. So much so that, for instance, in stage 4 is the metastatic stage. So like the cells reach the blood flow and can migrate to other organs. Now, studying the molecular determinants of this process means finding some genes, something that we can measure easily that can allow us to determine in which stage the patient is, and so reach, for instance, those more accurate diagnoses that we were discussing before. And this is particularly relevant, as we just heard, for breast cancer. So we are studying in the personalized medicine use case, specifically invasive breast carcinoma, which can have two anatomical location, mostly the ductal carcinoma, which is the more common, and then lobular carcinoma. And as you can see on the right, the different stages really determines different levels of 5-year survival. So, as it was said before, the earlier you are diagnosed, the better chances you have to survive, to undergo like treatments that are successful, while the management of patients in later stages is much more complicated, and you can see that there is actually a drop in survival if the tumor is diagnosed too late. So it is very important, and this is the main goal of our use case, to try to diagnose accurately an individual as early as possible, but also to try to understand where she is at, like maybe she's close to the next stage, or how long will it take for this cancer to progress to more, let's say, advanced stages. And is this like a fast-growing stage or a low-growing stage? So the tumor. So all, let's say, questions that we can address by applying the techniques that we are developing in EVENFLOW. And so the data that we are using for addressing these kind of questions comes from a very reputable public database that is the Cancer Genome Atlas, and it contains multi-omics data for several cancers, but we are in particular, of course, focusing on breast cancer. And the type of data, the type of omic that we are using is bulk RNA-seq, because we are interested in the expression of genes in order to identify specific pathways that are activated, deactivated, or in order to pinpoint specific biomarkers. But as it was said before, it would be also interesting to integrate like all the other omics in order to improve our performances. But for the moment, we are focusing on bulk RNA-seq. And after, like the usual pre-processing and the, let's say, preliminary analysis of the data, we can end up with a dataset that is that encompasses information for around 900 women. So like a nice large dataset. Now there is a catch though, that essentially this scenario is really very close to the type of scenario that I was showing you before, because in TCGA we have information for one patient that is in a specific stage, but then we don't have like a follow-up. So essentially we have like other information for another patient that is in another stage, and so on and so forth. So it's very scattered, and we have all those different snapshots in different moments of time that comes from different people. And so this makes everything even more challenging. And this is why I was saying that the type of studies that we are conducting and the type of methodology that we are conducting are actually trying to tackle a problem that is quite general, because unfortunately this situation is very common in biomedicine. So the first thing that we asked is, okay, can we train a classifier to distinguish between those stages? Which basically means how noisy, in a way, like how similar are those patients? Can we classify the different stages? And well, it turns out that in breast cancer, predicting the stage is actually a very difficult task for machine learning approaches and using RNA-seq. So here you have a comparison between the performances of an optimized classifier on those RNA-seq data in breast cancer with different performance score, compared to another type of cancer, which is kidney cancer. And you can see that in the case of breast cancer, the performances are quite disappointing. Those are quite low, which means that those classifiers, those machine learning classifiers, are having trouble in even distinguishing between stage 1, stage 2, stage 3, and so forth. While in other type of cancer, this task seems to be easier. So what is going on with the expression profiles of those breast cancer patients? So if we plot, for instance, all the patients in stage 1 and stage 2 in a low-dimensional space in order to visualize this data, these expression profiles, we can see that actually there is a very low separability. So all those different stages are, all around the place. There is not like a region in the space that is dedicated to stage 1 and the other to stage 2. Like it's actually like very difficult and very heterogeneous. So there is a global low separability. But what caught our attention is that if you zoom in and you look closely, a patient in stage 1 is actually like quite close in this transcriptomic space to a patient in stage 2, another patient in stage 2, which means that there are some kind of similarities, at least at individual level. And so we start thinking about this, and in a sense this somehow make sense, like biologically speaking, considering that a tumor is actually trying to survive in the host, and so we do not expect massive changes in expression between two stages. What we expect are subtle changes, maybe in pathways or genes that are important for the tumor to keep surviving, but also keep growing. So always consider, like it is shown, for instance, in these hallmarks of cancer. This has been shown many times, all the different, let's say, characteristics of tumors, like tumor progression, is that the tumor has to stealth from this hostile environment, especially avoiding the immune destruction. So based on this concept, we started applying approaches that are very close to the ones that I was showing you before, that are for single cell. The only difference is that in our case, we don't have individual cells, but we have individual patients. Okay, so specifically, we can draw pseudo-time stage trajectories posing, like, framing this problem as a linear assignment problem, as it is done for single cell when pseudotime trajectories are derived. So this basically means if I have a patient that is in a certain stage and her tumor has specific characteristics, I want to minimize a cost function that aim to find the most similar patient in the next stage. And if I do this for all the patients, I basically end up with this map that you can see on the right. And this map is telling us, possible transitions that goes from patient in stage 1 to patient in stage 2 to patient in stage 3. So in the absence of additional knowledge, this is the best that we can do in order to identify what is the most likely next step. And once we have this map, we can actually do many things. For instance, we can train an artificial intelligence system that is able to fill in the gap, which was actually the ultimate goal, right? So this artificial intelligence system is the type of model that we use is called variational autoencoder. It works like this. So essentially, you have the real gene expression data. You can encode this information into a lower dimensional space that is called a latent space. And then you can reconstruct this data into a synthetic gene expression data by sampling from this latent space. If you are sampling exactly from the same place as the real data, you are reconstructing the real data synthetically, but you are reconstructing exactly that. But if you are sampling from, for instance, interpolations or other regions in the space, you are creating synthetic instances. And so we can conduct this kind of using the map that I was showing you before to guide the production of this synthetic data that essentially are gonna be in between the different stages as based on the pseudo trajectories that we drew before. And so now we have this complete trajectory filled up with synthetic information that we can study. And in order to understand if there are some characteristics that are specific of the transition from one stage to the other. And this can be done, this type of analysis can be done in many different ways. And one way that we did this was to compute pathway enrichments in those genes. So basically, here we have a trajectory that goes from stage 1 to stage 2 to stage 3 with all those synthetic data in between that we found by training this AI model. And we are looking at the changes in different pathways. So one pathway in particular that caught our attention is the reproduction pathway. So series of genes that are involved in reproduction processes, and so affected or mediating also hormonal processes, which is very relevant for breast cancer. And we can see that in stage 1, essentially, we don't have much changes, but then heading towards stage 2, we see a progressive downregulation. And then when we go back to stage 3, when we progress to stage 3, this downregulation is lifted up. And we can make this analysis also for other trajectories in the map and also for other pathways. And importantly, getting the genes that are relevant for these patterns that we are identifying, allowing predictions and allowing forecasting. Of course, in EVENFLOW, we don't do just that. We are applying also other techniques, and also we are analyzing the different cancer types. For instance, we have a line of work that use multi-scale cellular simulations of tumoral growth using agent-based models, and this can be simulated for many different cancer types. You can see in the middle that we are also applying synthetic data augmentation techniques for medulloblastoma, which is a childhood brain tumor. And also we are experimenting with variations of the variational autoencoder, which is specifically a conditional variational autoencoder, in order to generate pseudotime trajectories that are conditioned to specific characteristics of an individual patient. So many different things that, being let's say in the second half of the project, we are trying to finalize, and we are trying to to get as much information, as much insight as possible, and from which we can also right now get some critical insights and takeaways. So first of all, we saw that the way in which we frame the personalized medicine use case is actually trying to tackle challenges that are common to the biomedical field, and that entails the reconstruction of dynamical processes from scattered snapshots in time. When this is applied to breast cancer, which is a very challenging scenario that is characterized by data heterogeneity and sparsity, we see that we can, like, applying those techniques in order to get molecular biomarkers, or like investigate the molecular determination of cancer staging specifically. And then finally, that a series of techniques that are based on artificial intelligence and that are drawn specifically from the single cell domain, like different types of representation learning, generative models, and so forth, can elucidate this dynamic processing, identifying biomarkers, and also facilitating the development of further models for predicting or for forecasting. So with this, it's all. I would like to thank again the EVENFLOW project, all of you for your attention, and also specifically Guillermo, who is a PhD in the group that is behind all this research in breast cancer for EVENFLOW. Thank you so much.
Thank you very much for your presentation, Dr. Cirillo. So I think that we have a couple of minutes for some questions, so we can open the floor for questions. Please feel free to type your questions in the chat, and we can address them to the speakers. Right now. Okay. We have actually a question. From Elena Siri. I wanted to ask, coming from an engineering background, what is the difference between oncotype DX genes and panel 50 for identifying the different subtypes of BRCA? Are these gene sets overlapping?
Okay, so these two gene panels are slightly different. Oncotype DX, it's only able to classify the risk of relapse of hormone-positive breast cancer. The list of genes of this panel is actually public. You can check them in their webpage. PAM50 is different. Not only provides the risk, but it also is able to tell you whether a specific cancer that has been diagnosed belongs to the subtype luminal A, B, HER2 enriched, or basal type. This is not possible with oncotype. However, the list of genes that are included in PAM50 has not been published. It's patent protected. When you run an RNA-seq experiment with a number of cancers in which the classification, is possible to come close to the PAM50, but the funny thing is that if you run it different times, you can narrow down to 50 genes, but sometimes some of them are there, sometimes are not. So probably there's a discrete, not an infinite number of 50 genes that can do this job. But exactly which are the 50 genes included in PAM50 is not publicly disclosed.
Okay, thank you very much. And maybe questions from me to Davide. How can the EVENFLOW technologies advance cancer research?
Yeah. So the overall the goal of the EVENFLOW project is to develop methodologies, as it was shown before by Thanasis, for forecasting complex event. This is the ultimate, let's say, methodological goal, specifically using neurosymbolic approaches. So this, of course, like it's very challenging, like the application of this is very challenging in the context of breast cancer specifically, and in general biomedicine, given all the limitations, no, and the unknowns that we have about the data. But still, we are seeing that by devising devising ways of deriving trajectories, of deriving extrapolating like these pseudo-temporal aspects from the data that we have, can allow the application also of neurosymbolic approaches. So specifically EVENFLOW as a project that is developing like this kind of techniques, we think that by complementing like those technologies with others, like for instance the ones that I show you, can lead to the application, to the successful application of these techniques, and also which is the most important thing, to get insights, even more insights about the scientific questions that we have.
Okay, thank you very much. So I think that we can now conclude today's webinar. I would like to thank you very much, our speakers, and all of you for your participation. Feel free to subscribe to EVENFLOW newsletter, to check our website for future events and news from the community. Thank you very much again, and I wish you a great day.
Thank you.
Thank you.
Thank you, everyone.